Hello, ChemFam. We are going to be discussing specific heat capacity today. Now, this is part of thermochem, and it's important because the specific heat capacity is really just the amount of heat it takes to change the temperature of a substance by 1 degree, and that's if you have 1 gram of that substance. So if you think about it, different things heat up in different ways. Some things are super easy to heat up. For example, if you're cooking at your house and you're using a metal pan, you put that flame underneath and that pan heats up really quick. But if you're going to try to boil water, it takes a while to heat up water. So specific heat capacity, which by the way is labeled with the variable C, all right, lets you know how easy or difficult it is to heat up a substance. Okay, now that's going to relate to a lot of different things we've already been talking about with Q for heat and energy and also change in temperature. So let's keep that in mind. When thinking about metals and nonmetals, water, strangely enough, has a really large specific heat capacity. What does it mean when you have a specific heat capacity that is large? It means it's pretty difficult to heat up or cool off water. Water retains its heat well. Think about Lake Michigan. When it's summer, all right, at night by Chicago, Lake Michigan, all right, at night the temperature dips outside because the sun went down. But by the lake it still stays warm in the summer. Why? Because the heat from the water is still there and it's slowly being given off, but it's always warmer by the lake in the night at summer than it is, out in the suburbs, okay? So the specific heat capacity plays a role in kind of the temperature and weather around an area too. But that means that since specific heat value for water is large, it takes a longer time to actually, cool off or heat up. So when we look at specific heat, all right, you'll see C was the variable I talked about, but it actually has an interesting unit of measurement. The measurement is joules per gram degree Celsius, and that's because it's including the amount of energy, the amount of mass of the object, and the temperature change. So it's a goofy looking unit of measurement, but it all works out in the end when we start doing calculations. Again, the other form of energy besides joule is a calorie. So a calorie per gram of substance per degree Celsius will also be a unit of measurement, and we'll look into that. So let's start looking at the different heat capacities of different objects. Here's a chart that you will become quite familiar with, and it's a specific heat capacity chart, and as you go up, it gets higher and higher. Remember, the higher the specific heat capacity, the more difficult it is to heat up or cool off that object. And look at the top. Water is one of the largest ones. In fact, ice still has quite a bit of specific heat capacity, and so does steam. Notice, though, that solid, liquid, and gas water all have different specific heat capacity values. Again, think of it like a rating. The higher the number, the harder it is to cool off or heat up that substance. But look at the bottom here, copper. Copper has a low specific heat capacity value, which means that it's really easy to heat up. I wonder if that's why we use copper pots for cooking. Yes, it's absolutely. When you put fire or a flame on a copper pot, it heats up quickly. Why does it heat up quickly? Because it has a very low value for specific heat. Its specific heat capacity is low, all right? So if you look around, obviously metals, which are good conductors of heat, tend to have lower specific heat values, and we'll see that nonmetals tend to have higher ones. Now, how does specific heat value relate to everything we've been learning about in thermochem so far, including heat or energy, the mass of an object, and also the change in temperature? Objects heat up or cool off if they gain or lose energy. All right, well, that's all related in this equation called Q equals MC delta T. Q is the heat or energy is equal to the mass of the object times its specific heat value, that came off of the chart we just looked at, times the change in temperature of an object. The change in temperature, by the way, which is right here, is always going to be the final temperature the object is at minus its initial temperature. And we know that a change in temperature, it might be negative. You may have gone from a now smaller number, so gone down in energy, minus the initial energy, which is higher. So that's okay if this number ends up being negative. It's not a problem. Now, it won't always be negative, but it's okay if it can be negative. So I better write that too, right? It can be positive as well. And the big thing is or. All right, so let's see if we can use this equation, Q equals mc delta T, to start figuring out some information about different objects. Here's a practice problem where we can apply specific heat capacity and everything we've learned about thermochem so far. So the temperature of a piece of copper has a mass of 95.4 grams. So first of all, I'm just going to write down all the pieces of information I've been given. 95.4 grams. It increases from 25 degrees Celsius to 48 degrees Celsius. Okay, so it started at initial temperature of 25 degrees Celsius. Now you don't have to worry about putting these in Kelvin instead of Celsius because we're just taking the subtraction between them, the difference between them. So degrees Celsius is fine. By the way, it ended at 48 degrees Celsius, so that is good. That means that that'll be our final temperature. And the metal absorbs 848 joules of heat. Now, heat or energy in our equation is going to be our Q. And again, we're getting used to that because these are our vocabulary words. So heat or energy is going to be Q. So we want to know what is the specific heat of copper. So specific heat, remember the variable for that is a C. So all these pieces of information are given and they're all related by this equation. Q equals, or heat equals mass times the specific heat times the change in temperature, which is final temperature minus initial. So can we start plugging in and chugging out different answers? 100%. So let's do it. The total energy is 848 joules. The mass is 95.4 grams. The specific heat, I don't know. I'm solving for it here. Now, what if you did get the specific heat or you needed it? You could always look on that chart like we had on the previous page. So that chart will be available to you. Sometimes you just have to look up the specific heat if you don't have enough information, all right? But in this case, we're trying to solve for it. Now, the final temperature is 48 degrees Celsius, and the initial temperature was 25 degrees Celsius. So we're going to put that all together, and we're going to start doing some of our math. If I subtract my temperatures, I now have 23 times C is 95.4 equals 848. Now I'm going to multiply those two together to get an answer. Multiplying those together gives me 2,194.2 times C equals 848. Now to get C by itself, I'm going to divide both sides by 2194.2 so that C becomes alone there. And I'm going to do that math. The answer I end up getting is a decimal, and it's not a pretty number, and that's normal for specific heat. It becomes 0.386. And if I look on my chart to get an idea of what my units are, it's going to be for specific heat capacity, joules per gram, degrees Celsius, okay? So we've applied a bunch of different ideas and put it together in one relationship. This is the relationship because of specific heat capacity. Again, the heat is equal to the mass times the individual specific heat capacity times the change in temperature. And from that, we can start predicting different things, not just specific heat, but a lot of other things. Maybe next time we could solve for final temperature, or we could solve for the change in heat or energy that happens. Either way, this equation helps us out. Again, an important thing though is to make sure you do know, what does Q mean? What does M mean? What does C mean? What does final temperature mean? And what does initial temperature mean? All right? If you can do that, you will be well on your way. The next thing we're going to be doing is definitely some practice problems. So hang in there. Thanks for listening, ChemFam, and best of luck with specific heat.